Hi everybody. I hope you're doing well. In the present lecture, our main goal is to find the density matrix, the Neumann matrix, and the average for the occupation numbers or for the number operator in the case of free bosons and free fermions. Okay, so first let us discuss some general aspects. So we will derive the Bose-Einstein and the Fermi-Dirac statistics. Let us just take into consideration a few aspects here. We are not our interest is not on correlated systems. So suppose the ket state of your system can be written as a product n1 times n2 times n3, which is a tensor product of states, okay, which can be represented in the number representation as a state with n1 particles in the state 1, n2 particles in the state 2, n3 particles in state 3, n4 particles and so on in state 4 and so on, and zeros for the unoccupied state. All right, so you have zeros for non-occupied states, and this is a given state with the occupation numbers n1, n2, n3, and 4. 1, 2, 3, 4, the indices here mean that you have quantum numbers. So suppose the psi can be written as a product, a tensor product over some j variable here, or alpha, perhaps the product of alpha, the occupation number at the alpha quantum number. So it's a product state. Okay, you can factorize the state of your system into the following form. So as a summation, as a product, of the kets and alpha, right? This is for our states. In assumption here, free particles or free fields in second quantized notation. So the assumption here is free particles whose state can be written as a product in the number representation. It completely neglects correlations in this approximation here. Right? Well, now let us consider first the case of free bosons. So now let us discuss as a first example bosons. Okay, occupation numbers for bosons in a given alpha can be 0, 1, 2, 3, for any integer, any positive integer. Okay, and the Hamiltonian for bosons is given by the following. Hamiltonian, it has the same form, as a matter of fact, for bosons or fermions. It doesn't really matter, but it is a summation over the energy in the state alpha, okay, summed over all the alphas of your system, times the number operator. I will use A, dagger alpha A alpha for bosons. Okay, and in the case of bosons, just remember commutators of annihilation operators or creation operators are 0, and the commutator of A alpha, which is annihilation operator for the state alpha, with the creation operator for the state beta, is equal to the Kronecker delta if the states can be labeled by a countable set of numbers. Okay, so it is a discrete set of states. If you have a continuous set, it is replaced by some integral over the energies. And this is replaced by a Dirac delta of the indices relating to those states. Okay. Now we want to calculate the density matrix, which allow us after that to calculate the mean energy of the system or the average energy and the number of the occupation number in the average or whatever physical quantity we want for the system. But first we need to calculate the density matrix in the canonical ensemble. So what is the density matrix in canonical ensemble? Okay, what is this matrix in the canonical ensemble? Well, first of all, for the whole system, for bosons, it is not too difficult to write the density matrix, the total density matrix, as the exponential of minus beta times the full Hamiltonian of the system divided by the partition function, which is just the trace of e to the minus beta times the Hamiltonian. This is for any given system, for fermions, bosons, or whatever. It is the partition function in the quantum statistics of your system. So this is called partition. Okay, so this is the partition. And now we can write the Hamiltonian here, which is the summation over alpha, the states alpha, times energy alpha times this Hermitian operator, which is number operator. Remember, the number operator is just the product. A alpha, dagger, A alpha. So this is the number operator. All right? And it is divided by a number, which is the trace. After you calculate the trace, you get a number, right? And in this case, just remember a property, since this commutes for a given alpha with a beta, this operator commutes. So if you have 4 fermions or 4 bosons, it doesn't matter if you have this. But in particular for bosons, here, this thing here commutes, and therefore the exponential of a sum can be rewritten as a product of the exponentials minus beta. Beta is the reciprocal temperature I am using here, but it's perhaps a bad notation. Let me use here lambda. Okay, so beta here, this beta factor here is the reciprocal of the temperature of the system. Okay, 1 over the Boltzmann constant times temperature. And therefore, if you have a exponential of a sum of functions here, you can rewrite it as e to the f1, e to the f2, and so on, which means the product of the exponentials over fj. So this is a product function of the exponentials beta to the e alpha, a dagger alpha, a alpha. It is divided by the whole partition function. Okay, the partition function is the trace of the overall quantity here. But notice that the total density matrix is factorized by this product. And now we can rewrite it as the following: a product over alpha rows of the quantum numbers alpha. And this is just the exponential of minus beta e alpha, and this is the operator, the number operator in the state alpha, divided by the full z partition function, which we can also rewrite as a product over alpha z's alphas. The z of a given alpha now is just a trace, a partial trace over this object here. Okay, so this is the partition function. And now, since we can write the Z matrix as a product over the entire set of quantum states, okay, they are just quantum numbers labeling the energy eigenstates. We have a product of over alpha of this object, which is a matrix, divided by the partition function of that particular operator. Notice that if you take the trace of this object, you have this trace divided by this, which is already a trace of that operator, and this gives 1, but it is a product of 1s, and therefore you have 1. So the trace of the partition function is exactly 1. And for any given alpha, the subsystem is already normalized. So the trace of a part of the total density matrix is 1. And therefore, the trace of the product is also 1. Okay. So what we need to do is to determine the rho alpha density matrix, which is the exponential over minus beta E, which is the energy of the system with the set of quantum numbers alpha, the number operator for that given state, divided by the partition function of that state alpha. Okay, this is the density matrix, and the whole density matrix is the product. I am using here it for bosons, but it is also applied for fermions. It doesn't matter if these operators A dagger A are bosonic or fermionic. If you can write the states of your system as a product state, if it's possible, then this is a valid result in the canonical ensemble for the density matrix. Now we need to evaluate this object here. What this produces for a given state of energy E alpha. Okay? So far so good. Let us insert the completeness in the number representation. So we have rho of a given alpha state is equal to the exponential of minus beta, the energy of that state, the number operator in that state, This is divided by the trace of this object here, which is the partition function for that specific state. And now we will insert here a summation over the numbers in the state alpha, which can assume for bosons, this is the only difference. For bosons, this summation runs from 0 to infinity. For fermions, this runs from 0 to 1. This is the only, really the only distinction between bosons and fermions here in this calculation, okay? So you have the completeness for the basis in that state, okay? So this is a completeness because you can have 0 bosons, 1, 2, 3, and this forms a diagonal matrix in the number representation. And this is for the given state alpha. You can have another state, but I am evaluating the density matrix for that given specified state. It could be atomic orbitals, plane waves, or whatever it is. And now, when you apply an operator to its own basis, it just reproduces the number, the eigenvalue. Therefore, you have e to the minus beta e alpha, a summation over n. Let me drop this alpha here because it's just an integer. So let me write it as n from 0 to infinity times n. And it is divided by the partition function n times n. Okay. Just I'm dropping out. I'm dropping this this index here because I am summing over from 0 to infinity in that state alpha. Okay, the alpha is specified in the energy here. Now, what we need to do, we need to calculate the trace of that state alpha, and the trace to find out the partition function is just, this is diagonal in number representation, so it is a sum over diagonal factors. This is something like the following. Okay, this resembles this matrix here. Zeros in the off diagonal terms, e to the n equals to 0, so it is 1 here. E to the minus beta e alpha, e to the minus 2 twice beta e alpha, e to the minus 3 beta e alpha, and so on in the diagonal. If you add these terms all together, you'll find out a summation over n from 0 to infinity, the exponential of minus beta e alpha times n. Okay, this is the partition function here, which is very relevant because, as we already know, if you want to calculate the average of the energy, you can calculate it from derivatives or differentiation of this function with respect to beta, and other physical quantities are just second order or first order, whatever, derivatives of the partition function with respect to the reciprocal of the temperature or with respect to some other variable here. So let us just work a little bit this expression here, okay? The partition function for bosons. So partition function for bosons in a state E alpha, okay? So this is the energy state alpha in a given quantum state with energy E alpha. Let me be here compact in the writing, but it means that there are a given number of bosons, which I don't know how many, in the state E alpha. And the temperature will say that in the canonical ensemble by an average. So I really don't know if there is 0, 1, 2, 3, but this is the partition function. This is the density matrix. And now we have the partition function. So what we are trying to calculate is this thing here. So this function for fermions, or sorry, for bosons, is given by the following: a summation over n from 0 to infinity, e to the minus beta e alpha times n. We can redefine this expression to the following: some variable x to the n from 0 to infinity summed over n, where this x is exponential of minus beta e alpha. Okay, why is that? Just because the exponential n times the exponential of minus beta e alpha, if you multiply this, is the same as just exponentiating this object here to the power n. All right, so this is another notation. But this object here, summation from 0 to infinity, is 1 plus x squared plus x cubed, and so on. And it is just the geometric series. It is 1 over 1 minus x. All right, so this summation has an exact representation, which is this fraction, 1 over 1 minus x. So the partition function for bosons at a given state alpha, this state alpha, we don't exactly know how many bosons there are. It is just 1 over 1 minus x, e to the minus beta e alpha. All right, this is the partition function for bosons. Okay, this is a very important result. It was not in the present form. It was derived first in the study of a black body radiation by Planck, which introduced this concept of quanta of a given unit of energy, E alpha. So you can have 1 unit, no units, 0, 1 unit of E alpha, 2 units, 3 units, 4 units, and an integer multiple of this quantity here. So this was not using this formalism of Bosonic algebra, not using this formalism of the density matrix, but Planck was the first one to derive an expression which looks like this thing here. As a matter of fact, I guess he derived an expression for occupation numbers, but since Bose and Einstein studied the distribution with more mathematical rigor, this distribution was named after Bose and Einstein, the Bose-Einstein distribution, which we will find in a minute, and related to the Bose-Einstein distribution, we have this partition function, which is the partition function for bosons. Okay, so now let us remember that the density matrix is written as a summation over the numbers e to the minus beta e alpha and n tensor product with n, and divided by the partition, which is just a number, 1 minus e to the minus beta E alpha, okay? Because this is just 1 over the partition function. We can divide any element here, all right? Now, let us calculate the average occupation number. Remember that the energy average, suppose there is the Hamiltonian of the alpha state, it is the average of this operator, A dagger alpha, A alpha. It depends on the occupation number average. Okay, so if we calculate the occupation number in the state alpha, we are by a multiplicative constant, which is the energy of the state alpha, we are calculating the average of the energy in that system. Of course, the full average of the Hamiltonian, which is the sum over all the states alpha, the average of the full Hamiltonian is just the summation over alpha, the values of the energies times the average, the energy of the state times the average of the number in that state alpha. So this is for a particular alpha. Here I am summing over all the states. So here, particular alpha, state alpha, and this is the average, the energy average. Okay, this is the total Hamiltonian, and this is summed over all states alpha. Now this is the full average of the Hamiltonian. This is the full average, the total energy average. Okay, but let us calculate for a particular state the average of the Hamiltonian, the energy average for a given state. Okay, to do that, we need to calculate the number average, and this number in the state alpha is just the trace of rho times the number operator, which can be commuted here because the trace has this property. So this is the trace of n alpha rho. And when you apply the number operator to a state with n particle, this just produces a summation over n times e to the minus beta e alpha n times n multiplied in the tensor form here, in the exterior form, sorry, and this is divided by this constant here, constant, no, this function of temperature and the energy of the state, which is the partition function of the state. But now, just this, I need to calculate the trace of this object, okay, the trace of this object, but this object is already in the diagonal form. Now, notice that the trace here corresponds to a summation over the entire possibilities of the n occupation number here for the state E alpha, n times e to the minus beta E alpha n, because this is the diagonal ones, which appears in the diagonal. Off diagonal there are zeros, and this is divided by 1 minus e to the minus beta E alpha. This is the partition function here. Notice that if we differentiate this exponential with respect to the beta E alpha, we have this n here apart from a sign, which is a minus, and therefore notice if we calculate the derivative with respect to beta E alpha, of this summation e to the minus beta e alpha n, summed over all the possible n's, what we find is a summation with a minus sign, because minus beta e alpha, or minus n, sorry, if we differentiate with respect to this variable beta e alpha, we have a minus n here, minus n, e to the minus beta e alpha n. Okay? And therefore, again, we have that this is the partition function. If you insert a minus here in front of the equation, you can switch this sign here, because minus the full equation produces the minus, the plus here. The minus sign is eliminated. And this is just the numerator here. So the number average, the occupation number in average, is just 1 over the partition function for that state alpha, a minus sign which comes from here, the derivative with respect to the beta e alpha, which is just the exponent here of the partition function z alpha, which is this object here. But this object we already calculated. It is, remember, z alpha is just 1 over 1 minus e to the minus beta e alpha. Okay, we already determined that factor. Now we can calculate the average for the occupation in the state n alpha. Okay, this is a distribution for the occupation, and in this case, what we have in the average, or on the average, we have 1 over 1 minus e to the minus beta e alpha, okay, minus. And when we derive this expression here, we need to calculate the derivative. We have 1 divided by 1 minus e to the minus beta e alpha squared, and it comes with a minus sign here. We can use the derivative of 1 over some equation here. So we have the square of the function, the denominator, the derivative of this times that, but the derivative of 1 is 0, minus 1 times the derivative of that. The derivative of this one is 0, this minus comes into place. There is another minus here, so minus 1, because we are differentiating with respect to beta e alpha, e to the minus beta e alpha, okay? So minus times minus is just one factor of minus, which cancel out this one here, this product of minus signs, and therefore we have the following equation. 1 over z, 1 over z. 1 over z is, the inverse of the z is, as a matter of fact, 1 minus e to the minus beta e alpha. Okay, this is what we have, the inverse of this function. I guess I did it wrong in the previous calculation, where I specified the function, the rho function. Let me remember the rho function of alpha. I had it written the following way: from 0 to infinity, e to the minus beta e alpha times n, divided by this factor. It is not divided because it's the inverse of the partition function. So this is to the minus 1, okay? I missed this minus 1 in the previous equation. Okay, just correct that in your notes. But here it's correct. It is the inverse of the partition function. The partition function is this object here, and therefore we can eliminate this because here we have the squared. We can eliminate the minus signs, so the minus is just cancelled out. We have e to the minus beta, the energy of the state alpha, divided by 1 minus e to the minus beta e alpha. And now we can multiply the numerator and the denominator by e to the beta e alpha, which just produces 1 over e to the beta e alpha minus 1. I think you can't see this. I am looking at the video here and the expression. I need to confine myself to this position, perhaps here. Exponential of beta e alpha minus 1. Okay, so this is the occupation number in the average, e to the beta e alpha. This is what is called the Bose-Einstein distribution. Okay, what is the number of bosons in a state with energy E alpha? It is statistically given by this equation here. Okay, therefore Bose-Einstein distribution partition function is 1 over to the minus 1 minus e to the minus beta e alpha for a given state alpha, and the occupation number on the average is given by 1 over e to the beta e alpha minus 1. Okay, this is the so-called Bose-Einstein distribution. If you are trying to calculate the average, the mean energy of a bosonic system, given the bosonic degrees of freedom and a set of quantum states labeled by these alphas here, you would have a summation over alphas, the energy of the state times the average of occupation number in that state. This is the average of the occupation number. It is an operator, so the average is this function here. So you have a summation over alpha, which corresponds to a set of quantum numbers, e alpha divided by exponential of beta e alpha minus 1. This is the energy average of your system. Okay? If you have a continuous set of quantum numbers, you need to replace the summation by an integral over energies. Okay? But now we can express as a graph this equation here, which was, as I mentioned, deduced in the context of black body radiation by Planck, Max Planck, around 1899, I guess. And the graph for this function is the following. We will use these expressions just to calculate for phonons or whatever, the bosons which we are dealing. So if you want to calculate the if you want to graph the equation, you have the following as a function of the energy here. You have a which is usually written as F BE here, just to remember Bose-Einstein as a function of the energy. It is the exponential of beta E minus 1. Usually for bosons, you write the energy as h bar omega, so it can be written as a function of omega or graphed as a function of omega. But now notice that for energies, finite temperatures, energies close to zero, this exponential is close to 1, and 1 minus 1 tends to 0, and this function explodes. And otherwise, it goes rapidly to 0 because this exponential grows with the increase of the energy. So the Bose-Einstein, perhaps, it is a function like this. Okay, so this is the occupation number. It goes like this. Okay, so for lowest energy levels, you have the occupation number given the energy, the quantum of the energy. If the quantum of the energy is very small and the temperature is finite, you have a number growing exponentially to infinity, all right? But if you have the energies higher, far higher than the temperature, the probability of occupation tends to 0. So for beta E greater, much greater than the unity, which corresponds, remember this beta is related to the temperature, which corresponds to a high temperature, or a high energy compared to the temperature. For high energies compared to temperature, this exponential fully dominates, or for very small temperatures compared to this energy here. And what it doesn't matter if you increase E or you reduce the temperature, it doesn't matter what you do. For E to the kBt much greater than 1, this exponential becomes much greater than unity, and you can drop out this 1, you can neglect this 1 here, and you have for the Bose-Einstein distribution approximately e to the minus beta e, the exponential of minus beta e, because you can neglect this 1 over this exponential becomes e to the minus the argument, and this is the Boltzmann distribution. So for high energies compared to the thermal energies, you have a Boltzmann distribution. But for this approaching unit, or this not so large, you have this Bose-Einstein distribution function. Okay, so in this scenario here, it approaches Boltzmann, which is classical. So a quantum system becomes, for these higher energies, a nearly described by a classical distribution function. Okay, so this is for bosons. Okay, let us now consider fermions. The main lines are the same. So fermions. Also, you can consider the Hamiltonian for fermions given by a summation over alphas, the energy of the alpha state, and the occupation number of that state. But now you have that the C alphas with C alpha primes or the C daggers, the annihilation and the creation operators, the anti-commute. But if you pick up a C alpha with a C dagger of alpha primed, I'm just uh, avoiding to use beta because it is related to temperature. So this is alpha alpha prime here is a Kronecker delta. Okay, this is fermionic algebra. You can set that the density matrix is a product over alphas, the density matrix over a given alpha. You also considering that the size of the system correspond to n1, n2, n3, a given number at the alpha state. All right, so this is a product state. It is a product state. All right, this product state, same as for bosons, which we discussed previously. And now the role alpha for a given state alpha corresponds to the exponential of minus beta times the energy of that state times the number operator divided by the partition function here, which is the trace of this object here, e to the minus beta, e alpha, c dagger alpha, c alpha. So this is for fermions. It looks like the same as for bosons. But now for fermions, just remember, for fermions, the occupation for a given alpha can be only 0 or 1. So the set of eigenvalues of this operator corresponds to two possible values, 0 or 1. The state must be unoccupied or occupied. You cannot put two fermions in that state. The maximum allowed number is 1 and the minimum is 0. And of course, completeness corresponds to 0, 0 plus 1, 1. This is the identity matrix for a given state alpha, okay, for a given state alpha. For all the alphas, for a given alpha, you have a 2 by 2 matrix, and for any given alpha. So for all the alphas, the reasoning applies, and this is the identity. This is the completeness relation or closure relation for the states in the number representation. And therefore, we can calculate this object here, which is the trace, the partition function for the trace of this exponential, which is the partition function for fermions. Okay, let us do that. And as a matter of fact, it is much easier than for the case of bosons because you have just two possibilities here. So partition function here, z alpha, is equal to trace. You need to sum up the diagonal of e to the minus beta e alpha times the number operator. Remember the number operator here. The number is just the product of C, which is C dagger, which is a creation operator, times C alpha, which is annihilation operator, acting on the summation over the number occupation going from 0 to 1, two possible states, 0 or 1. It is distinct from bosons, which goes from 0 to infinity. Now fermions, 0 to 1, n, okay. And this is a 2 by 2 matrix in the subspace of the state alpha, okay? For bosons, the submatrix in the subspace of the state alpha is an infinite dimensional but discrete matrix. Here we have a 2 by 2 matrix, all right? So there are two possibilities, and the two possibilities here correspond to eigenstate with zero fermions. I need to replace here by zero, and this is it in the diagonal form. So it is the trace of a matrix looking like this one. So this puts values on the diagonal, and for the state with zero particles, I have one here. For the state with one particle, I have e to the minus beta e alpha. So the trace of this matrix just corresponds to 1 plus e to the minus beta e alpha. Okay? This is the trace of that matrix. Okay? Now we can calculate the matrix, the density matrix for the state alpha. It is just a summation over n e to the minus beta e alpha n times this exterior product, but it runs from 0 to 1, and it is now divided by this factor because this is the trace, the trace of this matrix, which is the partition function. So 1 plus e to the minus beta e alpha. Okay, this is just what we have here. Okay, now the same arguments apply, same ideas apply for the given alpha state. The average of E alpha, C dagger alpha, C alpha, it is just E alpha times the average of the number operator, the total energy of the system on the average is just a summation over all the alphas possible, the energy of a given alpha times the occupation number given the temperature of the system. And now, if you try to calculate what you have, and alpha on the average, 1 over z of the state alpha, the derivative with respect to the beta E alpha, z of the alpha state, the partition function of the alpha state, of the subspace alpha. So this is the partition function. Now for fermions, this is a quite general expression, all right? And for fermions, we already know it is 1 plus e to the minus beta E alpha. So if we differentiate this equation here, we have 1 over the partition, 1 plus e to the minus beta E alpha. The derivative of this is the derivative of 1, which is 0. The derivative of this exponential, which produces a minus sign and repeats the exponential. But this cancels out this exponential here, so we have e to the minus beta E alpha. And we again are able to multiply by plus beta E alpha in the numerator and in the denominator, e to the plus beta E alpha. And we arrive at the occupation number for fermions at a given state alpha. Okay, so for a given state alpha, what we have is the following: Fermi-Dirac distribution. Okay, this is the Fermi-Dirac distribution. It corresponds usually, it is written as f, some distribution function of Fermi and Dirac as a function of the energy E alpha, which is equal now to 1 divided by e to the beta E alpha plus 1. Okay, this is the Fermi-Dirac distribution. And if you go beyond the canonical ensemble, you go to the grand canonical ensemble, you need just to insert, it produces the same result as a matter of fact, but for the grand canonical, you have in place of minus beta the Hamiltonian, you have to replace, this is the canonical, if you have the grand canonical, you need to replace e to the minus beta the Hamiltonian, and of course you normalize by the trace here by another partition function, of course, but you just need to use the minus beta times the Hamiltonian minus some chemical potential times the number, the total number operator here. Okay, so you can have a variable total number of particles in this system, and this is called the chemical potential of your system. You introduce an object. It is outside the scope of this course to discuss statistical physics, but just assume it to be valid. You introduce some chemical potential here. Chemical potential. The chemical potential is the energy necessary to take out or to put one more particle into the system. Okay, is the energy needed to do that. So how much the energy of the system varies if you remove one particle or if you insert one particle. This is the chemical potential is related to that. Okay, so in this case, if you go beyond the canonical ensemble, you define another ensemble which is called the grand canonical. You insert the chemical potential. It is not too difficult to show that. Here the energy is reduced, or you need to subtract from the energy of the alpha state the chemical potential. And in the grand canonical Fermi-Dirac, I am considering this for Fermi-Dirac statistics because it's more relevant to consider a chemical potential. So you have a chemical potential here. It is given by the following: e to the beta, the energy of the state alpha minus the chemical potential plus 1. Okay, it is just a redefinition of the energy. Notice each energy of the system is now just displaced by some factor mu. It is the chemical potential is subtracted from each energy of the system, and therefore the calculation is the same, but just you need to replace E alpha by E alpha minus mu for any given system. So the Fermi-Dirac distribution looks like this equation here. At zero temperature, at T equals to 0, the chemical potential is called the Fermi level of your system. Okay, so the Fermi energy of your system, or Fermi level. Okay. Now, the total energy of your system, the total energy, if you have a discrete spectrum, it is given by a summation over all the alphas, the energy of the state alpha times the occupation number, but the occupation number is given by this. Okay, and this function here, the Fermi-Dirac function, let me rewrite the Fermi-Dirac function, which is the probability of occupation at a given energy E is equal to 1 divided by e to the beta energy minus mu plus 1. this function we can plot against the energy or beta energy. This is the chemical potential. It is an important reference in the energy. Okay, and this is a Fermi-Dirac distribution given the energy and given the potential. This function, notice, if energies are much smaller than the chemical potential, for much smaller energies than the chemical potential, you have this number is very negative, and the beta for lower temperatures, for low temperatures, it is a small number because beta is 1 over kT. T is a small number, beta is a very large number. Okay, that's what I'm saying, to be clear. For low temperatures, beta is a high number. Okay, beta, remember, is 1 over kBT, Boltzmann constant times temperature. Temperature is low, beta is very large number. And if this is a negative number, this exponential is the total E minus mu is a negative number, and beta is very high number. You have the exponential of a very negative number, a largely negative number, and this exponentially is vanishingly small. Therefore, it can be neglected, and you have 1 over 1. So the probability, well below this value of the energy, is 1. Okay, so 1. Okay, 1. Now, if you have the energy exactly equal to mu, exactly at the chemical potential, this exponential goes to 1 because something which is equal to the other thing, when you subtract one from the other, you get 0. So the exponential of 0 is 1, plus 1 is 2, so 1/2. Exactly here you have 1/2 for the occupation number. Probabilistically speaking, you have 50-50 chance of that state of energy at mu to be occupied or unoccupied. And on the contrary, if the energy is much, much larger than mu, you have this exponential being dominated by beta E. So this exponential grows, and you have a vanishingly small probability. So it will reduce to a Boltzmann distribution, e to the minus beta E. If this term dominates and this energy is very larger than the chemical potential, you have just a Boltzmann factor. So in the large energy, this is just a Boltzmann distribution, and therefore you have something like this. Okay? For a finite temperature, you have a smeared function here. Okay, you have something like this to be more realistic here, but this graph is it decays to 1/2 exactly at the chemical potential. But if you are considering 0 temperature, it is a step-like function. Okay, so it is a step-like function exactly at the chemical potential. You have the Fermi energy. Okay, Fermi energy for temperature equal to 0, and this is a step-like function. So for all the energies below the chemical potential, you have states which are occupied by one fermion, and for all the energies above the chemical potential or the Fermi level, you have all the states unoccupied at T equal to 0. But if you increase the temperature, some of the fermions can have energies higher than chemical potential, and they are removed from here. So this area here is equal to the area here. Okay, these areas are equal because the amount of fermions you removed for energies lower than mu will be found. You'll find them in the spectrum of energies above the Fermi level or the chemical potential of your system. So this area here is equal to that area if you are considering that the total number of particles in your system is unchanged. Okay, so if the system has a definite number of particles at temperature T equal to 0, your distribution is a step-like function here. It goes from 1 to 0 abruptly at the chemical potential. Probability of finding particles here is 1. Probability of finding particles here is 0. But if you increase the temperature, some particles here close to the chemical potential, but nearly below the chemical potential can cross that level and will be found here in higher energies, and this amount is equal to the net particles which you removed from here and put into here. Okay, so if you are considering that the total number of particles is constant in your system. So the Fermi-Dirac distribution is step-like. For t equal to 0, exactly 0, you can rewrite the Fermi-Dirac distribution in the following way. 1 if, so that function is 1 if the energy is below the chemical potential, 0 otherwise. Okay, and exactly at mu, you can consider it's 1/2, or in some instances you can approximate by 1 or 0, but on the average it is half. Okay, so for energies higher than the chemical potential, 0. For energies lower than the chemical potential, 1. It is very abrupt. There is a discontinuity for the energy exactly equal to the chemical potential. But if you consider a finite temperature exactly at the chemical potential, you have a 50-50 chance of finding an electron or whatever the fermion is occupying that state. Okay, and the total energy of the system, if the spectrum is discrete, you sum over alpha. If you have a continuous spectrum, you need to integrate here over alpha. So in next lectures, we will discuss a little bit more about that. I am finishing here. So what we have found the Bose-Einstein distribution, we have found the Fermi-Dirac distribution. These functions are very important in the description of solid materials, the temperature behavior of materials, for electric charge transport, for the description of many physical properties of semiconductors, of metals, of insulating materials, for description of the magnetism in the materials. There are a lot of properties which depend if the system is not strongly correlated, as in the case of perhaps a quantum Hall effect or superconductivity, if they are a strongly correlated system. If your system is not on those very distinct states which shows correlations, show very strong correlations, if you are in a situation where you can write the state of the system as a product of occupation numbers at any given state, right? So the probability of finding the particle in one state is independent of finding the another particle in another state. So there are no correlations. You can use Bose-Einstein and Fermi-Dirac distributions. They are, in the case of fermions, they can be interpreted directly as a probabilistic function. For bosons, they are related to the number of bosons in that state, okay? And it is linked, directly linked to many physical aspects of many body systems, of solid state, okay? And we will use that in our future lectures, okay? Hope you could understand a little bit what I am trying to bring to you, and I'll see you next time. Bye bye.